Hello everyone and welcome to our next lecture. This is Module 3, so we're making good progress in this course and I hope everyone's doing well. Hope you are staying safe and you're staying updated with the course. Hope you're not having too much issue. Of course, please always get in touch with me if you are. So let's just get right into our first lecture for this module, and it's on the birth of mechanics. And I'm not talking about the guy that fixes your car. Um, But mechanics is this old word for the branch of science that deals with the motions of material objects. And that's this, kind of like high verbiage to say rocks rolling down a hill, a touchdown pass that's thrown through the air, a home run hit over the wall, the sailboat skimming over the water. Those are all fit subjects for this kind of science. For years and years, philosophers speculated on the reasons why objects in the sky or just on Earth itself move the way that they do. But it wouldn't be until the 17th century that our scientific modern understanding of mechanics would begin to emerge. So, this is Galileo Galilei, and this is one of his actual telescopes that he built. And Galileo used those telescopes, and he, by the way, he just built them based off how somebody described them to him. He was a very influential scientist, and he was able to use those materials, those telescopes, in order to come up with a lot of great discoveries. Um, Before I talk about, what we're getting into, Galileo did a lot of things. He invented the thermometer, the pendulum clock, the proportional compass. He was also, like I said, the first to record observations using that telescope. And those astronomical observations and writings that he produced, he then later used to support the Copernican model of the universe. And if you remember what that is, it's saying that the sun is the center of the universe, not Earth. Now, this would later lead to him being tried for heresy by the Inquisition, and often it's depicted as, this noble scientist that was sort of, kept down by the man of the time, which was the church. And that's somewhat true, but it's not to say that Galileo was unable to work or was completely shut down. He was able to get this work out by, going under the ruse of, well, it's just a hypothesis and things of that nature. But he was also the kind of person that liked to be the thorn in the side of people influential, like the Pope. And one of his famous writings, he had a character who was this, basically the village idiot. And the village idiot would be spouting off things in his writing that were obviously words that the Pope had used. And so he kind of brought the Inquisition upon himself. Um, it wouldn't be until the late 90s where the Vatican actually gave him a posthumous not guilty charge. But it's just an interesting thing to think about all of this. This is not a history course by any means, but just interesting to talk about. Now, Galileo didn't just look at things in the sky and support the Copernican model of the universe, but he also studied moving objects. But in order to talk about that, we're going to have to lay some groundwork so that we can really just understand what he actually studied. So let's start with getting three precise definitions of important terms: speed, velocity, and acceleration. So speed I define as the distance traveled by an object divided by the time it takes to travel that distance. Velocity, I said, the same numerical value as speed, but it's a quantity that also includes information on which direction the object is traveling. Okay, so velocity and speed are pretty much the same, but when we talk about velocity, we also say which way it was traveling. So the speed of your car might be 40 miles per hour. So the time it takes to travel that distance, but it's also the distance traveled. 40 miles and how many per hour? 1 hour. But your car's velocity would be 40 miles per hour due west. Okay, so it's just adding that directionality onto the speed. Quantities like velocity that have both a speed and direction we call vectors. Okay, so if there is a directionality to it, we call it a vector. Velocity and speed are both measured in units of distance per time, usually meters per second, or when we talk about science. But we in the United States use feet per second and miles per hour, which are not used worldwide. Obviously, the metric system is the scientific and most of the world's preferred system. Meters per second, kilometers per hour, things like that. What we get is this basically a way to define velocity. This equation is what I'm looking for there. So v obviously is for velocity, distance measured in meters, and time. So distance divided by time, miles per hour, or meters per second. In this case, meters in second. That's usually what we will use in science, is meters per second. That's just the simple equation for velocity. Velocity is a distance over time. Okay. But the third one is acceleration. And here is acceleration, which is a measure of the rate of change of velocity. So whenever an object changes speed or direction, it has to accelerate. If you step on the gas on your car, you obviously feel your body hit the back of the chair, and you know that you are speeding up, and that's an acceleration. But if you step on the brakes, you also accelerate, just backwards. Now, normally we call that deceleration, but it is just an acceleration in the opposite direction of which you were originally going. Acceleration is the amount of change in velocity divided by the time it takes for those changes to occur. So here's the acceleration formula. And just like the velocity formula, acceleration, we just said, has a direction. So it's a vector. And when velocity changes, depending on how quickly, it could be any number of meters per second per second. Did that make sense? So you speed up or slow down some number of meters per second every second, right? So think it's kind of what I'm trying to get at is that the units here are meters per second squared, because let's put it in miles per hour. If I accelerate 5 miles per hour every second, does that make sense? So you could change how many meters per second, and you accelerate 10 meters per second every second. That's why it's meters per second squared, okay? Hopefully that makes sense, but if not, try to ask me. And also, you could just understand that when we talk about acceleration, the units we have to use are meters per second squared, because you're changing your velocity, which is obviously velocity meters per second, but you're doing so in some amount of time, which is another amount of seconds, so meters per second squared. So let's talk about this founder of experimental science. For many years, Greek philosophers had taught that heavier objects must fall faster than light ones. And they're philosophers, right? They're not really scientists. They're kind of just using reasoning. And it stands to reason that if it was a heavier object, it would fall faster than a light object. But that's not science, that's reasoning. Now, many scientists in today will now view Galileo's greatest achievement as his experimental work on the behavior of objects that are thrown or dropped on the surface of the Earth. Galileo was able to devise really just ingenious experiments to determine the relationships among distance, time, velocity, and acceleration. By the way, Galileo, he's technically famous for supposedly having dropped two objects from the Leaning Tower of Pisa to show that they fall at the same rate. But historians actually don't think that ever happened. Um, it's kind of trumped up to be really really amazing, but he may not have ever actually done that, and it's what he's most famous for. Um, but what did he actually do? What do we know that he for sure did? Well, he did a series of these classic experiments, and through them he was able to show that at Earth's surface, all objects accelerate at the same rate as they fall downward. And so, how did he do this? Well, first of all, it was necessary for him to be able to accurately measure two variables, distance and time. Now, back then, you have to understand they were working with far inferior technology than, of course, we have today. But he was still going to be able to easily measure distance using rulers. But their timepieces were just not accurate enough at the time to measure a quickly falling object. So instead, he constructed this apparatus you see on your screen right now that would allow him to slow down the falling time by allowing the balls to roll down an angled plane crafted of brass and hardwood. So instead of just dropping them, he allowed them to slowly roll down. He was convinced that any object accelerating toward Earth, no matter how heavy or light, will fall with exactly the same constant acceleration. In other words, the velocity of an accelerating object that starts from rest is proportional to the length of time it has been falling. And in equation form, right here, velocity is constant acceleration times time. So there's a constant acceleration that will multiply by the amount of time. And here's basically what he built. It was probably very similar to something that looks like this, where these brass or metal balls would roll down this plank and they would make some kind of noise that he could listen to in order to basically accurately measure the speed. And because the human ear is really, really good at picking up noises that may or may not occur at the same rate. So basically, Galileo's experiment tells us that if an object is falling for 2 seconds, it achieves a velocity twice that of an object that will only be falling for 1 second. And if it's falling for 3 seconds, it'll have 3 times the amount of velocity of an object that's only falling for 1 second. The exact value of that velocity depends on the acceleration, which was controlled by the angle of the ramp at the time. And he would increase or decrease that ramp. But in the special case where the angle of the ramp was 90 degrees, so basically the object is just falling, that acceleration becomes so special that in mechanics it's given its own letter of the alphabet, little g. Okay? I know up here it says big G, but it's little g. Okay? Little g is the acceleration of all objects that all of these objects experience at Earth's surface. You could kind of think of it, of course, as little g meaning gravity for Earth specifically. Little g is actually equal to negative 9.8 meters per second squared. It's the acceleration an object in free fall on Earth's surface will experience. And so take a look. In 1 second, an object will have reached exactly negative. Why is it negative? Well, because it's going downwards. If for some reason it was going upwards, it would have a positive acceleration. Okay? But at 1 second, it'll be 9.8. Well, if you double that in 2 seconds, negative 19.6, and so on down the line. And so Galileo's experiment with the ramp holds true to even free fall. Then Galileo comes up with his third equation. It demonstrated that the distance covered by an accelerating object depends on the square of the travel time, or basically the distance traveled in meters, equals 1/2, just 0.5, times the acceleration, which is meters per second squared, times time squared, or seconds squared. Basically, here's what that equation looks like. Distance equals 1/2 times acceleration times time squared. So armed with those three equations that relate distance, velocity, acceleration, and time, scientists were now poised to study motions of objects on Earth and also just throughout the cosmos. So it's pretty easy just to think, well, those equations are pretty simple. But the amount of work that had to be put in order for those to actually be made and to be proved true is incredible. It's the most obviously the most incredible work ever done because it's laid the foundation for everything else that's come. Okay, so let's get into Isaac Newton and the universal laws of motion. Now that scientists, like I said, had Galileo's work, they could begin to isolate and observe the motion of all material objects in nature and begin to summarize their results into mathematical relationships. So enter English scientist Sir Isaac Newton, one of the most brilliant scientists who ever lived. He's able to synthesize the work of Galileo and obviously others into statements of the basic principles that govern the motion of everything in the universe. Let me say that again. He makes up a bunch of sentences that basically says this is how everything in the universe works. So, yeah, pretty important. These sentences basically are called Newton's laws of motion. Remember that whole thing about, what's a law? A law is the truth of the universe. And though they're going to sound basic, you have to remember that these are going to forever change the landscape of science itself. So let's talk about the first law. A moving object will continue moving in a straight line at a constant speed, and a stationary object will remain at rest unless acted on by an unbalanced force. Okay, what does that mean in English? In other words, objects in motion tend to stay in motion, and objects at rest stay at rest. And you already know this is true. Swing a lanyard of keys around your head. It will only go in a circle while you are applying a force. But if you let it go, it will fly out in one direction. And when that object is traveling in a straight line at a constant speed, we say it's in uniform motion. All other motions are called acceleration. So if it's moving but not in a straight line, it must be accelerating. The tendency of an object to remain in uniform motion is called inertia. And a force is something that produces a change in the state of a motion of an object. So if you're going to stop an object from moving, stop its inertia, you must apply a force. You got to hit the brakes. You got to, stop it from moving somehow with another force. The second law. The acceleration produced on a body by a force is proportional to the magnitude of the force and inversely proportional to the mass of the object. Okay, in other words, what does it mean? The greater the force, the greater the acceleration. But the more massive the object being acted on by a given force, the smaller the acceleration. And you know this as well. It's easier to lift a child than it is an adult. You could pick up a child with one amount of force, but that amount of force will not lift the adult, right? The more massive the object, the adult, being acted upon by the given force, the same force that can lift the child will not lift the adult. What is the equation for this? Force equals mass in kilograms multiplied by acceleration. Mass times acceleration equals a force. So here's a question. What is the force needed to accelerate a 75 kilogram sprinter from rest to a speed of 10 meters per second in half a second? Okay, so first we know, here's our force. What is the force needed? So we're going to use this. Force equals mass times acceleration. But in our question, it's asking for the force. We don't know it. So obviously this is the equation we need to use. We do have a mass, but it doesn't tell us about an acceleration. So we can't plug in A. We can plug in M. We have the mass, 75 kilograms. So we've got to go back and use the acceleration equation from a few slides ago. Acceleration equals change in velocity over the change in time. So what's the change in velocity? Well, from rest, so just not moving, 0 meters per second to 10 meters per second. Okay, so we put 10 meters per second, which is our final velocity, subtracted it from our original velocity of 0 meters per second, and divided it by change in time, a half a second, 0.5 seconds. So 10 minus 0 divided by 0.5 gives you 20 meters per second squared. Okay, that's the acceleration that you need to do, that this would produce. Now, let's talk about what force that produces. In order to do that, take your acceleration, take your mass, multiply them, and you get the force is equal to 1,500 newtons. Newtons are the unit for force. So that's pretty impressive that you get to have your last name as the unit for the thing that you define. And so hopefully this makes sense to you. You get a question here. It says, what is the force needed? So you know that you need to use the force, not like you're a Jedi, but you need to use the force equation. The force equation is force equals mass times acceleration. We have the mass, but we don't have an acceleration, so you have to find the acceleration. How do you find the acceleration? Use the acceleration equation, change in velocity over change in time. You put the final velocity, subtract it from the original velocity, divide it by time, get your answer, plug that answer into the force equation, and you get your force. Okay, let's keep moving. The third law. For every action, there is an equal and opposite reaction. We've heard this before. Maybe not talking about Newton's laws, but maybe more colloquially. But whenever a force is applied to an object, that object exerts an equal and opposite force back onto you if you're doing it. You can feel this. Push your palm against a wall, and the wall will push back equally and opposite in your direction. You will feel it pushing against your palm. So sentences like the car slammed in the tree or the tree stopped the car's motion are both correct because both things happened. Now, what's important to understand is that the same force applied onto an object, same force applied onto two different objects can have very different consequences. If you're driving along the road and a bug hits your windshield, the force of your car hitting that bug splatters it across your windshield. The same force is applied to your very, very large car comparatively to the bug, and there is some tiny, infinitesimally small rate of deceleration from that bug hitting the windshield, but you don't notice it. The bug is destroyed, absolutely, turned into goo, and your car doesn't experience anything. Okay. The next thing that I'd like to talk about is momentum. You've seen, so basically Newton's laws tell us that the only way to change the motion of an object is to apply a force, right? And we all have the innate understanding of this, right? If I showed you a train was coming, you would get off the tracks, even if that train was moving 2 miles an hour. It would still be extremely hard to stop a train. Go ahead and be my guest and try, but you won't. At the same time, even very small objects can be very hard to stop if they're moving very quickly. Think of a bullet. I don't think you want to stand in front of a bullet when it's shot out of a gun when it's moving that quickly. However, if I threw a bullet at you, that's not going to kill you. Certainly, maybe it'll give you a little bruise, but it's not going to kill you. And so, intrinsically, we know if an object is in motion, the higher the speed, and also the heavier it is, the harder it is to stop. And physicists call this linear momentum. And the equation for momentum, by the way, it doesn't get an M because mass gets an M, it gets a P. Momentum equals mass times velocity. So even if the mass is very small, but the velocity is very high, like a bullet, it has very strong momentum. But if the mass is very high, even if the velocity is small, it still has a very strong, very high momentum. So here's the question. A baseball with a mass of 0.15 kilograms moves to the right with a velocity of 30 meters per second. So we've got all we need. What is the momentum? 0.15 kilograms times 30 meters per second gives you 4.5 kilograms per meters per second. And that's the momentum. Now, what does this mean? It means that in order to send this baseball out the other way, you've got to hit it with at least that amount of momentum. Well, if you hit it with exactly that amount of momentum, it will just stop. You've got to hit it with more momentum in order to send it the other way. Okay, hopefully that makes sense. Getting close to the end here, I promise. You've seen the consequences of this law of the conservation of linear momentum the last time that you watched a fireworks display. Okay? A firework works because a rocket flies up into the air and eventually reaches a moment where its momentum becomes zero and it becomes stationary at the top of its flight, and then it explodes. And all these brightly colored burning bits of material fly out in all directions. And, mathematically, if we could take every single one of these little pieces and we added all of their momentums up, it should cancel each other out and equal zero. And so what does this conservation of linear momentum really mean? It means that if we've got a 1 gram piece of material moving out this way at the right at 10 meters per second, there should be another on the left doing the same thing. And so that's why these fireworks get their symmetrical starburst shapes. It's because of the law of the conservation of linear momentum. Pretty cool. So not just linear momentum gets conserved, but angular momentum as well. An object that's rotating will keep rotating unless some sort of force acts on it. There's the twisting force called torque, and the more torque you add, it could cause that to stop, or you could add some other force intrinsically, from the outside that would cause it to stop as well. Now, interestingly enough, if you change the distribution of mass of an object that's spinning, it can change the spin rate. So what you'll see in skaters is that as the skater pulls her arms in, her momentum has to remain constant. So her spin rate increases to compensate. And so there's really a lot of cool videos of this that you can check out if you've never seen these skaters do this trick where they change their center of mass and it makes them spin even faster. So that's the conservation of angular momentum. And so with that, I'm going to end it here. There's one more lecture coming for this chapter, and I will see you in that one.